Hello everyone and welcome to our talk Knowledge Management and Anonymization Techniques in Cyber Threat Intelligence. This slot will be split into two separate talks, the first of which will deal with knowledge management and will be given by Mehdi Akbari Gourabi, and the second one will be held by me, Lasse Nitz, and will mainly deal with anonymization techniques in SAPAN. So I will now hand it over to Mehdi to hold the first talk.
Thank you, Lasse, for the introduction. Hello, everyone. Welcome to our talk. As Lasse told, this is the first part of the talk. It would be about knowledge management in cyber threat intelligence. I will first talk about context and motivations, and then knowledge modeling, and finally about knowledge management in our project. Cybersecurity information is generated in different institutes and organizations for different goals and values. They are generated by different approaches, tools, sensors, and applications, following different formats and standards, and a considerable part of this information is organization specific. Threat intelligence knowledge contains data patterns represent the incidents, also assessments related to them, for example, prioritizing the incidents for response based on the probability of true positive answers, and so on. And then the response and recovery steps to deal with the incident. The frequent response and recovery actions usually collected as playbooks. The question here is how to capture, reuse, and manage all this knowledge in this domain from all the tools, all the organizations, and so on. A good solution with many benefits would be knowledge modeling. Okay, what is knowledge modeling? Knowledge modeling is a graphical representation of knowledge with hierarchic structure. The idea of knowledge modeling is not only collecting the data items, but also express the relationships between them. The example of knowledge modeling would be knowledge graph, linked data, and semantic technologies. And the benefit of knowledge modeling is making data machine readable, more usable, and interoperable. Here we can see an example of graph representation of data. That's a very basic graph showing basic connections of an incident. Let's call incident X. It has different indicators of compromise, is a phishing attack, is still active, and a playbook is assigned to it. This graph can be represented by semantic technologies, basically by RDF triples. RDF is the fundamental semantic technology represent data in triples. It has different serialization formats such as XML, JSON, and turtles. A strong query language named Sparkle is available for query on RDF graphs. There are some extensions on RDF which provide additional semantics and make representation and modeling of data easier and more flexible. RDFS adds classes and properties, subclasses and subproperties, and domain and range. And additional concepts like cardinality, restrictions, transitivity, inverse property, and so on are provided by OWL too. In the next slides, I'll talk about our approach for knowledge management. For developing our response and recovery approach and also our vocabulary, we use Semantic Media Wiki for rapid prototyping. Semantic Media Wiki is an extension on MediaWiki which allows us to store and query on structured data in a wiki. Also, it adds machine readability to MediaWiki, improves its data structure, for example, by RDF Sparkle backend, and enabling a complex query by Sparkle. It also supports graphical display of information. Also, we develop our preliminary vocabulary to test the tool and collect feedback from domain experts by interviews. Feedback will be applied for further development, and the final demo of the tool will be provided with the final vocabulary. We can see the class relationship diagram of our preliminary vocabulary in the next slide. As we see here, the main classes here are incident and playbook. Incident class is connected to different classes like attack category, indicators, attack means, and so on by different properties. Also, a playbook consists of different steps that chain together. Each playbook will have one initial and one final step and a set of intermediate and exclusive choice steps, and might have some optional steps too. The steps are connected by has next step and has previous step properties, and optional steps are connected to intermediate steps but by has optional step property. Exclusive choice steps are using for decision steps and also enable exclusive branching. Here we can see the form by which we can enter a playbook in our semantic media wiki. As we see here, with different properties, we can connect our playbook to different classes. For example, connect them to different incidents and attack categories. And also, we defined three confidentiality level: public, partially confidential, and fully confidential for our playbooks. For privacy and confidentiality aspect, I have 3 points here. One aspect is related to different roles. Then we should have different permissions and visibility levels, which would be done by defining the user roles and access restrictions. The second point is that knowledge should be shareable between organizations, but this knowledge includes confidential data. Therefore, an approach to separate shareable part and unshareable part is really important and also challenging. And the third point is respecting data confidentiality is a recommendation of response and recovery action between organizations would be fundamental to security orchestration, automation, and response in a shareable and federated way. Basically, in any level that we consider sharing information or knowledge between organizations, we will face with privacy issues. In the next talk, Lasse will talk more about privacy aspect and solutions for a different part. Thanks for your attention. I'll hand it to Lasse for his talk.
Thank you, Mehdi. I will now continue with the second part of this slot and talk about anonymization techniques in cyber threat intelligence, especially in the context of the SAPAN project. Regarding the structure of this talk, I will first give a brief motivation and talk a bit about the context in which we can apply privacy-preserving technologies in SAPAN, and more specifically, I will talk about two scenarios. Then, as a specific example of such a privacy-preserving technology, I will quickly introduce URL generalization, which we applied within the context of SAPAN, and lastly present some initial results. The focus of this talk lies on methods for the transformation of data to allow privacy-preserving sharing among organizations. This has the huge benefit that it allows to share intelligence that has previously been considered to be not shareable, for example because it contains confidential information or because of data protection regulations. As two specific scenarios in SAPAN in which we can apply such methods, we have identified on the one hand the identification of phishing URLs. The problem with this is that given a URL, does it point to a phishing website or does it not? And the chosen approach was to train a binary machine learning classifier on URLs. On the other hand, we have the detection of domain generation algorithm activity, and quite similarly tries to solve the problem that given a certain domain, has this domain been generated by a domain generation algorithm or not? And again, the approach is to train a machine learning classifier, but this time on domains, and we consider both binary and multi-class classifiers. This now allows us to identify common ground between these two scenarios, and specifically we use a similar method in both cases. So for both of the two scenarios, we use machine learning algorithms for the goal of classification, and we also use similar input data. So we will consider domains as a specific version of a URL by saying it has an unspecified scheme, an empty path, an empty query, and an empty fragment. These two scenarios also share the same problem, and that appears if we want to share the machine learning classifiers, because training data could be extracted, for example, via membership inference attacks. Our goal is now to share these classifiers in a privacy-preserving way, meaning in this abstract scenario, organization O0 wants to share the trained classifier via the SAPAN platform with many other organizations, O1 to ON, and even if we consider one of them as being an attacker who tries to extract training data from this trained classifier, he cannot retrieve any meaningful information. More specifically, without applying any privacy-preserving technologies, the process of sharing the classifier would look something like this. The sharing organization would have a collection of training data, which it then uses to train the classifier that is to be shared, and the receiving organization then utilizes this classifier by feeding their own URLs for the call of classification to that classifier. One way to improve privacy in this context is to apply preprocessing to the training data with the goal of hiding or removing confidential information from the training data, and then use the modified data as training data for that classifier. This also means that the receiving organization, if it wants to feed URLs into the classifier for classification, needs to apply the same preprocessing before feeding the URLs to the classifier. Consequently, we do not only need to share the classifier, but also the preprocessing procedure. We consequently have to assume that also the attacker has access to this procedure and thus have to construct it in a way that it is not reversible. As one specific method that fulfills this approach of applying preprocessing, we have designed a generalization technique for URLs, which follows the general ideas that we want to completely generalize the scheme. This was mainly done to avoid that the machine learning classifiers develop a bias towards discriminating HTTP sites in the case of phishing classification. Further, we want to mask the domain and we want to decouple path content from path structure, which means that we want to remember how a path looked like in a structural sense, but we are not interested in the actual path content. And lastly, we want to remember whether a URL contained a query or a fragment, but we are not interested in the actual content of these. The result of this will be a pseudo URL that fulfills these criteria. So more specifically, we completely generalized the scheme by replacing it by star. For the domain, we wanted to mask it in a similarity-preserving way, meaning that two similar inputs will generate two similar outputs. For this, we used an approach by Schnell, Bachteler, and Reier, which they created for privacy-preserving record linkage, and this approach uses Bloom filters to mask different, in our case, domain elements separately. Only the top-level domain remains unchanged in our case. For the path, we want to replace each part of the path by structural information, meaning that we split the path at each slash and remember the length and the character alphabet used for each of these path elements. So, for example, whether it's an alphabetical path element or a numerical path element, and so on. For the query and fragment, we simply want to replace the query or fragment by the respective word query or fragment to remember whether it has been part of the input URL or not. So to give a better idea of how this looks like, consider the input URL as given on the slide, and for the output we completely generalize the scheme by just replacing it by star. This allows us to also take URLs as input which have an unspecified scheme. The domain then gets cut at each dot, and each of the domain elements will be transformed into Bloom filters, except for the top-level domain, which remains unchanged. So as indicated by the triple dots, you can see that usually, depending on the length of the Bloom filter, the domain increases drastically in size after applying preprocessing. For the path, we cut the path at each slash and consider each of the resulting elements as equivalent if they have the same length and use the same predefined alphabet. So for example, block gets mapped to the let for char, meaning that before preprocessing the entry consisted of 4 characters from an alphabetical alphabet, meaning that it only contained letters and no numbers or special characters. For the query and fragment, we only remember whether they were contained, and if so, we replace them by the word query or fragment respectively. To get an impression of how this transformation into pseudo-URLs impacts the accuracy of the respective machine learning classifiers, I will now present some initial results. We are currently still evaluating the possibility of potential biases in the training datasets, so please take these results with a grain of salt. In this diagram, you can see the results of the phishing classifier and 2 training datasets. So DS1 is a set of URLs without path information, and DS2 contains full paths. The respectively anonymized version then is extended by the suffix gen, so DS1 gen is the generalized version of DS1. And as machine learning approaches, we have used convolutional neural networks, CNN, and recurrent neural networks, RNN. So as you can see, applying URL generalization in all cases has a slight impact on the accuracy of the machine learning classifier, but not in a way that it would have a drastic effect on the utility of the respective classifiers. However, it is to note that applying URL generalization to a dataset with full path information yields way better results than using a raw dataset without path information. In this diagram, you can see the initial results for the binary DJA classifier, and as you can see, this achieves rather high accuracies. It might seem at first that applying URL generalization actually improves the accuracy of the machine learning classifiers. However, in practice, this is probably the result of randomness in the machine learning process. Overall, in all observed cases, applying URL generalization for the goal of binary DJA classification did not have a notable impact on the accuracy. Regarding future plans, we will further investigate the possibility of biases in the training data, and we will also take a look at variations of the presented approach to URL generalization. We further might look into alternative approaches to ensure privacy in such a context, for example, differentially private machine learning or machine learning on encrypted data. And with that, I end my talk and want to thank you for your attention.